So hello and welcome to my session. My name is Rastislav Szabo. I'm a software engineer at Valent, recently acquired by Cisco. And today I'll be speaking about BGP in Kubernetes. Why something like BGP may be useful in Kubernetes, and how can you use BGP in Kubernetes with Cilium. So before going to Kubernetes world, let me just give you brief introduction into what BGP actually is. So BGP is Border Gateway Protocol. It's a dynamic routing protocol which was designed to form the internet, to exchange the routes between what we call autonomous systems. And it turned out that nowadays is also very popular in the data center networks. It is an INTF standard, so it's highly interoperable. And it has been powering the internet for many decades. The first sketch of the BGP protocol was done in 1999. I was 2 years old at that time, by two engineers on the back of 3 ketchup-stained napkins. This is a pre-production of one of them. So it's a very old but proven protocol. The main use or the main reason for deploying BGP into a network is to exchange routes between routers, between BGP peers. Two routers first needs to form a peering, so they need to connect via TCP, and through the TCP connection, then they can exchange the routes. Those routes can be either IPv4 or IPv6 routes or some other protocol, network layer reachability informations. And those routes can have many attributes attached to them, which can be very useful for some advanced traffic engineering or affecting the packet path towards the way you need it. On the picture, you can see 3 routers. They are paired, so A is paired with B, B is paired with C, and the router A sends an BGP advertisement with a directly connected network to it towards the router B. And then router B can send a similar advertisement with the same network to router C. And conversely, router C can send an advertisement about its directly connected network to router B, and B can forward that to the router A. And this way, the routers learn about the routes, and at this point, all 3 routers know about both networks and how to get to them. Another important aspect of BGP is the notion of autonomous systems. So BGP autonomous system is a group of networks with some common routing policy for connecting to other autonomous systems or the internet. Autonomous system is usually operated by a single organization. It may be some internet service provider, large enterprise, university, government agency, and similar. And between the autonomous systems, we do have something that we call eBGP peerings, external BGP peerings, through which the autonomous systems exchange the routes between themselves. And internally within autonomous systems, there can be iBGP or internal BGP peerings through which the routers within AS can learn about the routes between themselves. And this is basically the way how we form the internet. The only difference is that we have many more autonomous systems than these 3 that you can see on the picture. And how many of them we have on the internet? It's many of them. This is a map of autonomous systems in the Europe's part of the internet, which shows individual autonomous systems and how they are paired together. And this one shows the entire internet. Altogether, right now we have more than 117,000 autonomous systems in the internet. So that's BGP for the internet, but why do we need something like this in our Kubernetes clusters? So let's first talk about data centers. Let's say you are building your own data center, and in the modern data centers, you would nowadays mostly see this kind of network topology. It's called closed network. It It consists of multiple tiers of switches. Here you can see spine tier of switches and leaf tier of switches. And each spine switch is interconnected with each leaf switch here on this picture. This gives us rich connectivity, uniformity, fault tolerance, and easy scaling. It's very easy to add more switches into such topology. If we wanted to achieve even larger scale, we can introduce more tiers, and this way we can achieve almost unlimited scale. But you may have noticed that we are starting to have quite so many links in this kind of network architecture. So how can we deal with them? Let's first think what would happen if we just connected these switches as standard layer 2 switches, right? So if all those links would be just layer 2 Ethernet cables between switch ports. What would happen? On layer 2, we run, or switches usually run something that is called spanning tree protocol, which breaks the connectivity matrix to a loop-free tree. Why? Because in layer 2 networks, we cannot have loops. Otherwise, we would soon see broadcast storms. So such kind of layer 2 interconnect between those switches, between spine and leaf switches, would not be very effective because many links would become unused actually. So on this picture, the green ones, for example, would be used and the red ones would be blocked. So not ideal. What's even less ideal is what would happen if one of the links would fail. Then the packet path can become very ineffective or inefficient. If you take a look at this picture, after a link failure, between the bottom left server and bottom right server, you would need to go through 4 hops to reach the destination. So how we can deal with these issues? The answer is easy. Instead of layer 2 between the switches, we would use layer 3 interconnection. And we would do routing on each one of the switches, on the spine and leaf level as well. That allows us to have all the links active all the time. And whenever there is a link failure, all the remaining links still become active and we have much higher throughput. But if we need to have a routing between so many switches, we need a routing protocol or too many static routes, but we wouldn't probably use static routes for such deployment. And it turned out that BGP is a very good routing protocol for this use case. Because first, it's relative simplicity. I mean, BGP is a complex routing protocol, but for like simple use case, as in this data center example, it's quite easy to bring it up. Also, another benefit is the scale. So it's proven that it can scale to the internet scales, right? So you won't have that scale in your data center. There are many existing implementation, even in the open source world. And they are all interoperable, so that there is no need to worry about that. And it supports many protocols. So through BGP, you can advertise IPv4, IPv6, and many other protocols, and it's easily extensible. And last but not least, it allows for advanced traffic engineering through path attributes. So that means that we can tune how the packets should flow in your data center very easily. But the question is, what if you still need some layer 2 connection between your routers? So we do have routers on the bottom of these pictures we do have servers on the bottom of this picture with 2 different VLANs. And we still want server on the left side to talk to the server on the right side on the layer 2 level. Let's say you have some kind of legacy application which needs that. How can that work if the links between leaf and spine are now layer 3 links? Well, that's also solvable with BGP. We can bring up VXLAN tunnels between the leaf switches, and via BGP we can actually advertise those layer 2 reachability information as well. So BGP can help also in this kind of layer 2 over layer 3 tunneling. And I think the most important use case of BGP in the data center in terms of Kubernetes deployments is equal cost multipath load balancing. So what it is, on this picture we have one router and we have 3 nodes, and each of the nodes is paired with the router, and each of the nodes would advertise the same virtual IP address to the router. So the router would learn the same prefix from 3 different sources with the same cost. And what the router does when there is an ingress traffic coming to that VIP is that it would start load balancing between them. And this way you can build load balancing in your infrastructure without the need for some specialized appliances because routers can do that very effectively on hardware. Okay, and now let's think about BGP in the cloud networks. Do we need BGP in the cloud if everything in the cloud is managed by the cloud provider and we don't need to care about it? Well, the answer is yes. There are some use cases for BGP even in the cloud networks, but they are a little bit more advanced. For example, in AWS, you can configure or you can play around with BGP if you are using either AWS Transit Gateway, Direct Connect, or side-to-side VPN. Basically, if you need to interconnect your cloud infrastructure with some on-premises infrastructure, then BGP can be helpful in case that you want to have redundant setup. Similarly, in Azure, there is BGP support on the Azure VPN gateways. Again, if you need to interconnect your on-premises sites with cloud infrastructure, then you can use BGP to build fault-tolerant setups. And again, similarly, in the Google Cloud, you can use BGP on Cloud Router, and you can use it again to interconnect between the cloud and on-prem. Okay, now finally let's go to Kubernetes. So Kubernetes can run either on in your on-premises infrastructure or in the cloud. So let's take a look at BGP in Kubernetes with Cilium. And I'm repeating this slide because this would be the main use case of BGP in the Kubernetes environments. So let's assume that the nodes down here, ABC, are your Kubernetes nodes. Then you can use BGP to advertise either service IPs or pod IPs towards a router and build an ingress load balancing solution for your setup using it. How can you do that? With Cilium, we do have BGP Control Plane built in the solution. You just need to enable it by one Helm flag. And it's fully integrated with all the Cilium features. So with kubeproxy replacement, all the IPAM modes that Cilium supports. It's Kubernetes-native, meaning that you can configure it via CRDs. There is no need for hard-coded IP addresses as much as it is possible. And most of the configuration is driven by labels. And it allows you to advertise Kubernetes-specific routes or prefixes to configured peers. So those can be Kubernetes services or podsiders. On this picture, we can take a look on how you can achieve that. So in Cilium, if you want to configure BGP, you would deploy a CRD called Cilium BGP peering policy. And this CRD is node-specific, meaning that you always need to select nodes to which that policy applies. You do that via node selector, in which you can match nodes by label. On this picture, for example, we have like 6 Kubernetes nodes, and 3 of them are deployed in rack 0, and 3 of them are deployed in the rack 1. And we want to peer the nodes in the rack 0 with the router B and the nodes in the rack 1 with the router C. So we deploy 2 Cilium BGP peering policies. One is selecting, matching the labels of the nodes in the rack 0, and the other one is matching the labels of the nodes in the rack 1. And inside of the BGP peering policy, you define your peering, your neighbors, addresses of your peers, and more details about the BGP peering if necessary. Once you have your peering set up, you need to configure Cilium and tell it what kind of routes it should advertise to the router. The simplest thing that you can do is turn the flag export pod CIDR to true, and that would advertise the pod CIDRs of the nodes to the routers. On this picture to one router, but it can be multiple routers in more complex deployments. As you can see, each node uses a different pod CIDR. Pod CIDR is a subnet from which we assign IP addresses to the pods. And each node advertises its pod CIDR to the router, so that the router knows where a given pod, where a traffic to a given pod should be routed. But I think the main use case is advertising service IP addresses. So in Kubernetes, you can deploy services for your workloads. And those services can be either load balancer services, cluster IP services, external IP services. All of them we can now advertise with Cilium. And the way you do it is that you configure the Cilium BGP peering policy again with the service selector, which is matching services that you want to advertise to the router. And as you can see on this example, we do have 3 Cilium nodes. Each one is advertising the same service IP to the router because either they do have backends for that service, or the service is configured to advertise it unconditionally. And whenever there is an ingress traffic coming to that service IP, then the router applies equal cost multiple path load balancing and load balances between the 3 nodes. Okay, so what I have just shown you was what we call BGP v1 API. That's the BGP Control Plane API that you would find in Cilium, in the latest Cilium version right now. But in the upcoming Cilium version, we will actually introduce a new BGP API that we call BGP v2. And we are making it a little bit more complex. It will no longer be just a single CRD. This time, there will be 4 CRDs, user-facing CRDs. And the reason is that we need to provide more flexibility for more advanced use cases for which the single CRD approach was not enough anymore. And another reason is that we also want to avoid some repetition that you would need to configure in case of a single CRD. So it looks complex, but it doesn't need to be necessarily that complex for simple use cases. If you just want to configure a simple BGP peering as similar to what I've shown you using BGP v2, then essentially you need to configure at least 3 CRDs. One is called Cilium BGP cluster config, which is like a definition of BGP cluster, BGP instance, ASN number, and the list of peers. And from the peer configuration, you reference another CRD, which is Cilium BGP peering config. That is peering configuration that can be much more complex than what you see here on the slide. But the main reason for this separate CRD is that you can reuse the same peer config for multiple peers. And from the BGP peer config, you reference another CRD, which is called Cilium BGP advertisement. And through that CRD, you control which routes you want to advertise, right? So in this example, we do have one Cilium BGP advertisement, and it tells Cilium to advertise podsiders and attach something that we call BGP communities to those routes. And then we have another advertisement type called service, and it contains some service-specific configuration, matching of the particular services, and again, some additional optional BGP attributes that you can attach to those routes. So basically, you can configure different kind of advertisements for different peers and for different BGP instances. Okay, if you want to try BGP with Cilium, it's quite easy. You don't necessarily need to have a BGP-enabled router. You can go to Cilium.io labs, and there are plenty of labs that can run in your browser, and some of them are actually using the BGP or showcasing the BGP control plane, so you can play around with it. We do not have Cilium BGP v2 lab yet, but it will come soon. And yeah, I think we have some time left, so I would show you a short demo of Cilium BGP v2 and how it works in actual cluster. Is this working? Yes. Okay, so here I have a cluster, quite empty cluster with 2 nodes. And BGP is enabled on both of the nodes. This cluster is now running BGP v2, which we can check by grabbing of API resources. And I've mentioned one of the BGP v2 CRDs is called Cilium BGP cluster config. That's the most important one from which you are starting your deployment. So in the Cilium BGP cluster config, we define a BGP instance, we define what's our ASN number, and we define the peers, peer IP address, and then with the reference peering config, which is saved in another CRD. So let's take a look at Cilium BGP peering config. Cilium BGP peer config contains the definition of the peering itself. So, for example, here it is configured as multi-hop BGP connection. We define which kind of advertisements, whether IPv4 or IPv6 we want to advertise, graceful restart configuration, etc. So that is like very specific BGP configuration for the given peer. And the third CRD is Cilium BGP advertisement. And in this one, we configure what IP addresses or prefixes we want to advertise. So we do have this podsider advertisement and service advertisement here. If you just want to advertise them, it can be much simpler than what you see here. This is just to showcase what kind of specific configuration you can put into the advertisement. So here we are putting some BGP attributes on the advertised routes and similar. So if you want to verify that your BGP configuration works, we do have Cilium CLI as well for debugging or working with the Cilium clusters. And there is a command called Cilium BGP peers, which shows you what peers have you configured via CRDs, what are the IP addresses of the peers, what is the state of the session, uptime, and how many routes are we receiving and advertising. And if you want to check what kind of routes are being advertised, there is Cilium BGP route command for that, which shows you per node which prefixes are being advertised. So if I showed you services from this cluster, then we should find some match. For example, this load balancer service is 10.2.53.169, and we see it advertised from this node and this node as well. And I have one router paired with these two nodes. This is FRR routing container, free open source BGP implementation. So I'll show you that the BGP neighbors are configured and BGP peerings are established with Cilium. And if we check show IP BGP, then we should see all the routes received from the Cilium nodes. Okay, so this was a very short demo. I think we can try to answer some questions. Let's take a look. Is Cilium advertising service IP only from nodes where services pods are located? Yeah, this is a good question. The answer is yes and no. It depends on what is the external traffic policy of the service. If the external traffic policy is clustered, then that service is advertised from all the nodes. If it's local, then it's only advertised from those nodes which have the active endpoints for that service. Our network department requires us to make BGP peering within specific VLAN where LB service return traffic needs to be routed back through some VLAN. Can Cilium do that? Yes and no. I mean, it's not built in directly into Cilium, but you could terminate the VLAN on some sub-interfaces on the node, and then let the node to form the peering through that sub-interface, and then the traffic should be entering through the sub-interface as well. So it requires a little bit of manual setup on the nodes, I would say. BGP is known as a slow routing protocol when used for advertising AS. How is it twisted so it's usable in more dynamic Kubernetes world? Yeah, absolutely, it's usable. So BGP has a bunch of timers built in, and those default values for those timers are not really designed for data center use cases. But you can tweak those timers also on in Cilium configuration to just few seconds, and in that case, like the failure detection can be literally within 2-3 seconds. You just need to tweak the timers. The default values for the timers are not really good for data center deployments. You mentioned the close topology. Is there a plan to integrate BGP EVPN extensions? Not that I would be aware of at the moment, but the good news is that with the BGP v2 kind of rewrite of the control plane, we have built very solid foundation for such more complex use cases. So if somebody from the community is interested, or if there will be demand for it, it can be done quite easily. Not easily, but it can be done. But no current plans for BGP VPN. What's the relation between Cilium and Cisco ACI CNI? I would say at the moment not a lot of relation, apart from the fact that both are CNIs. They are completely different CNIs. What is the maximum number of peers you can have in BGP cluster config? There is no limit. Your resources of your servers are defining the limit. What I've personally deployed was few thousands of peers, and it was working fine with them. but there are some future plans for addressing large-scale deployments to achieve less, to allow less peering configuration or configuring less peers, but no current like ETAs for that. And is BGP v2 just about configuration separation, or are there any new major features? It's only about configuration. The backend is like the control plane is still Go BGP, but that configuration separation kind of allows for some more features that were not possible in the past. But BGP v2 itself, as it will be released in the upcoming release, which will happen sometime in the summer, will not introduce any new major BGP feature. Only the API, like new API for the same feature set. But future-wise, of course, we've done that with for some reasons. And one of the reasons was to be more future-proof and to allow for more extensibility, but not in this release. Yeah, that's it. Thank you.